So, last time we finished the topic, what was that? Quantifiers, and we finished that by looking at the generalized De Morgan rules, at least in case when we considered the sets in question as the subsets of a bigger set where we just had the case where the set theoretic difference of the sets with a given set, of the union of the sets, in this case, or of intersection of the sets, respectively, was just the complement in this bigger set, respectively, and we just looked that it kind of swaps around. So we have the union and we take the complement of it, then we can transform it into an intersection by the cost of just swapping around in the sense of taking the complement of each of the sets that we had the union of. Right? Right? That was exactly this thing. But this was just an example of where we use the quantifier in the quantifiers in definition and also in the proof. But all in all, we have introduced the quantifiers and we have introduced after that the index sets. And before the quantifiers, we finished the topic sets after considering certain identities between set operations that were just yielded by the corresponding identities of the logical statements, right? So in total, we have now finished the three topics. The topic logical statements was the very first one, and the topic sets, and then the topic quantifiers. And we are finally by the last topic of the very, very basics, after which the standard basics are covered, or at least in one view you could say that the standard basics are covered. And the last topic that we have yet to cover is the topic maps. I hope that you have internalized the discussion, or more precisely the framework of the first three topics concerning understanding and concerning working intuition that is presented in an active fashion so that you can see how things work and how you can prove things in that setting and what goes, what doesn't go, and how the structures interrelate and so on. It's difficult to describe in words what exactly, but this is an approximate description. Having that in mind, we start the last topic of the very preliminaries of university maths, that is the maps. Alright. Oh. Now let's make it bigger. Okay. For maps. And first comes, of course, the definition of a map. Now, you might be a little bit surprised if you already heard of maps and if you know that a map is kind of a generalization of a function that assigned real numbers to real numbers in what you know, right? Let me change it a little because I didn't get it. Definition map No, not like that. Oh, so I don't get why it's so. Oh wow. Okay. Okay, I think I should increase the thickness of the line, but I'm not. I'm not getting now. Okay. Here. Right. All right. Now it works. Yes. Right. 3. Let's say 4. Let's try it out. So, a map is a triple, just like an ordered pair. Now, an ordered collection of free objects is called a triple. And it is a triple of the three following mathematical objects: x, y, and f. And don't be confused by this, introducing that as a triple or the triple of three objects. You'll understand in a minute why it has to be like that, or at least you understand what I'll be saying about that. And in a while you understand why it has to be like that and why it has its justice. A map is a triple x, y, f of a set x called, so the first set in such a triple is called the domain of f. A set y called the value space or target space of f. If you recall, a function or a map is just an assignment that assigns to every element of a set. I mean, if you recall from school, this definition fits. We just making it precise. That is an assignment that assigns every element in a set. In your case, it was always the set value numbers. A number in another set, and in your case, both sets will are. And in this case, the sets could be arbitrary, but there is a certain requirement. We'll talk about it in a second. the value space target space of f of the function and an assignment rule to x for x x y. Oh, well, let's maybe state it precise immediately so that it does not confuse you. So it would be okay that it is not written very precisely. And an assignment rule recall the quantifiers. For each x element x, and recall this one, that meant there exists exactly one. There exists exactly one y and y. Such that f assigns, and this is just intuitively interpreted, f assigns to the x this y. Right. So we recall what that meant. That meant we go through each one separately. That is, we fix an x tilde, element x. We just took any element out of x, and it exists exactly one y in y. So if we fixed an x tilde, element x, then there exists exactly one y, element y, such that f assigns to this x tilde that is now fixed this y. Then we take another like x hat, right? Element x, and then again there exists exactly one. It could be the same, doesn't matter, because the only thing that we care of for this now fixed element of x, there exists exactly one. How they interrelate between each other, like here was one y, call it y tilde, here is one y hat, and maybe y tilde is one is y hat, we don't care. The only condition is for each x there is exactly one y in y that is assigned by f to this x. That is the only condition. And follow it in your mind very precisely. Don't confuse it with, well, if y is given to one x, then this y is given and can't be used anymore. That's not that. That's only that for each chosen x, and each x must be chosen once, as we see here. For each chosen x, for each chosen x, there is exactly one. So for each there is exactly one, but it does not mean that for each y there is exactly one x. It's two different things, right? It's exactly that. We go through all x and we fix an x. For this x, f assigns to this x a unique y. That is, informally, this is really important. That's why we'll spend some time thinking about it. That is sometimes a source of confusion. That is what is happening informally. Clear input and the set of all inputs that we can choose is exactly x. Clear input gives uniquely determined output via f. You can think of it as a computer program that for each input gives you a clear output without any variation. If you know the input, you know the output, or you do not necessarily know, but you know that the output will be just exactly determined by the input, right? So you don't want to have that you inputted x and one time your computer program gave you y1 and another time it gave you a different y2 as output. This is a function, just that. And if you recall the coordinate system, but now imagine it is an abstract coordinate system. Here are just all elements of x. This is not r, this is x. Just imagine it abstractly. X could be anything, but just imagine it very abstractly without thinking exactly what it means to draw it. And that just means, well, this x, if I fix an element x, let's say x0 something, I mean, I'm just fixing some element of x. And just like in your usual Cartesian coordinate system, I have to pick one point that corresponds to it in the other set. And correspondence is one-sided, right? The correspondence is not that it is correspondence in sense of uh, correspondence with equal rights, but the correspondence is one-sided. I took one x and I fixed it and I get exactly one y. But it is of course possible that for another x I get the same y. What is not possible, that for this x I somehow get two, so that I cannot decide. I kind of cannot decide, is it the one, is it the other, is it both at once? That is impossible by a function. Okay. And of course, you have noticed, or hopefully you have noticed, that we have not defined that. So I just told you, well, this is logically clear. And of course it is clear. It is an assignment, okay? It is an assignment rule. We just say, if we are given such x, what f gives into correspondence with it is a y, element y, and for each x such a y exists and is chosen and is fixed. So the choice, when f is chosen, the choice is fixed, just like a written computer program with clear outputs for clear inputs and unique outputs for unique inputs, right? But, well, how do we formalize that exactly? Well, in truth, such an an assignment rule is again just a set of special kind. F is indeed a subset of a Cartesian product. Recall Cartesian product is just a set of pairs x, y, ordered pairs, where x is the first element in the pair. Any element of x can be chosen as that, and y is second element of y, element of y, of course, second element in the pair, and all such pairs are considered. This is a subset of this, and actually almost always a subset that is really contained and that we write like that. And this is a subset like that. X f of x, and f of x, of course, could be replaced by y, but this is just how we write it. Well, maybe let's write it for now like this. That we can introduce, and then we can rewrite it. But first, let's be a little bit slow. Okay. That's a subset of this, so this element is supposed first to be an element of the Cartesian product. But now, with the following conditions, right? Um, well, what do we require? Well, oh well, actually, we should now impose this condition of unique existence of such a y for x. And the question is how we do that. Well, we should require that okay, how do I formulate that? That's a good question. Because being in this set, it's kind of okay. Let me think for a little while. The thing is, I would have to refer to this set to define this set, but this is of course improper. Okay, this is such xy element of this. that I have to refer somehow to the whole multitude of those pairs. You see, here we already see something that I'd like to touch. That this definition is something very special, a definition of a function in general. If we'd like to just define it as a set, and we'd like to require that this set F is such a subset of the Cartesian product that it contains for each x, right? For each x, it contains a pair with only one y in y. But how do we describe that if we really say, well, that such elements of x cross y that, well, we have to refer to all of them at once, right? But then we have to refer to this set to describe it. Well, maybe you do not quite understand what I mean, but well, we have to use tricks to do that. We have to describe this set implicitly. So you recall what subset is, right? And now let's not yet give this set as a description, but let's postulate this set is a subset. Right. I could not describe it as a set because I'm giving a general definition of a function. So I can't describe it as a particular set. I have to describe it as a set with a property. Sorry for the confusion. Of course, I can't do that. I have to describe it as a set with a certain property. And well, how do we do that? Well, that's a subset of that. That's the first property that the function has to have. And now there's a second property. It is first a subset of this Cartesian product. And now it is a subset such that for all x x, of course, just same thing. There exists unique y element y, but now same thing properly. Assignment means building ordered pairs such that xy is in F. Right, now F is just a set, namely a subset of the Cartesian product. So a collection of pairs of this kind. And now what pairs? Well, a collection of pairs so that this collection satisfies the following property, that for all x in X, there exists exactly one y element y with xy element F. More precisely, F is then, well, let's state it. State an equivalent thing. For all and x for all y and y. For y tilde, so take two of them. Y have xy x y tilde, both in f, implies, and that goes like that, of course, implies x y equal xy tilde. And recall what the equality of ordered pairs was. It just meant that the first is equal to the first, the second is equal to the second. So that y is equal to y tilde. And this is just like a fancy and abstract way to write this here. And what does that mean? Well, that means exactly what we said above. The assignment for each x of a y is unique. But how exactly does it work? Well, it works like that. The Cartesian product can be, of course, written as just think of x as index set. We can do that, right? But here it is very straightforward, right? Can be written like that. And now what is f? Well, f as a set is just, we take such a thing for some x0, and we take an element of that, right? x0, and we just take some pair of those pairs where we just have x0 paired with all elements of y. So this is like the first element of f, then we unite it with, we take second element of x, and of course it could be just that we can't go through the elements of x in the way of first, second, and so on, because it's more than natural numbers in some sense. Then it's just an abstract procedure that which you don't have to connect to first step, second step. It could be as many steps as we like, just to for you to internalize with different probability and so on. And we just go through all such sets, and for each such set we just decide, we take this y, well, this is the pair that goes into this set. And after we have gone through all such sets and have taken, so we finish that and that, take one of them and so on, we have defined such f. Right, and you see, there can be quite many f's that satisfy that, of course. So quite many functions from x to y. But each of them is just defined in this fashion, and the difference is just, well, what element of the whole set y we decided to pair with particular x's, right? So in total, that will give different functions. Okay, and after we have discussed the formal definition, but yeah, well, in practice, it usually almost always, not always, but almost always suffices to think of it just as an assignment. But well, there is also the formal definition, and that's important to know. And in some contexts, the formal definition will also be used. But do not think of it necessarily too much. Just think about how it makes sense and what we'd like, as what we'd like to have it to use it properly in particular contexts, and that will show you what interrelationships between structures are important here, right? So it might seem very abstract somehow, but it's really not that abstract. You just have to get used to it. And now I have to take you on a detour because the topic of maps generally is of great importance to me. And if you'd like to skip that, then just skip that. But it is like it is a great opportunity to see what a big world that is, what I'm about to talk about. Right. Um, you see, a detour about maps, or a detour, yeah, a detour about maps. Well, how do I start? You see, we said that a map is kind of an assignment rule. That is, a map is something like we take any object of any kind in a certain collection, and to this object we assign something in another collection, even though it might be not warranted in any way at all. So it is a very artificial forcing of a relationship, of a kind of one-sided relationship, of assignment relationship between two groups of objects, or more generally, actually, if we do not specify the groups of objects in mathematics, it is specified, but more generally, it is just assignment of an object to an object. And now, if you think about it, then you understand that all the things that we have developed, languages, any system of communication, all science, that it is all based on this very fundamental principle of creating artificial relationships, of exactly this kind of assigning a meaning to a word, assigning a meaning to a sequence of sounds that we produce, then assigning a meaning to a sequence of words, then assigning a meaning to symbols. Everything what we have ever built and what we have ever thought of is distinguished from the nature world that surrounds us by those artificial assignments. We came up with them, and in the beginning they were completely arbitrary, but the circumstance of the possibility of making those assignments, and the circumstance of us having made those assignments of primary words to sounds that we made back then when we were not that far from the animals. This is what started our development as a species that is able to abstraction. You see, the nature world doesn't know any kind of artificial assignment relationship. In the nature world, this is simply not present. This kind of simplifying out an object and saying that this object has something to do, which that actually is, just that we describe almost always more or less precisely what it has to do with that in our view or how we'd like to view it. This simplifying out and assigning is what makes the distinction between the abstract intelligence and between the immediate perception of the world around us. And it is really important to me. Don't think that this does not have anything to do with maths. It has, and it has a lot to do with maths, but we will come to it in a little while. So you see, everything is based on this artificial assignments. That is my thesis. But now, here comes the maths. And if you are not familiar with some notions that I will talk about, well, I'll probably link that in the description. You can read about it. Don't be afraid. This is what you are here for, to just expand your horizon. In maths, we very first, of course, have the natural numbers. It's the counting numbers. It's just what our ancestors came up with to count objects, right? And also naturally, if you like, draw the natural numbers on the number line, then you could wonder, well, could I go into the other direction, right? You just position yourself on a road and you go into one direction on this road, and you think, well, I can go into the other direction, and I could call that, of course, like that. But now if I go two steps in that direction, two steps in that direction, if I would like to know where I am, how could I deal with those numbers? And this arises, not the notation arises, but the concept arises. And of course, historically, it might have risen a little bit differently, like loans might have given rise to negative numbers. That's not what I'm talking about. I'm talking about this being a very natural thing to think of. And of course, from those integers, you get very easily to the rational numbers. It's just, well, some fractional parts of things, like, yeah, it's like dividing things up into equal parts will eventually lead to a notion of fractions, and having this, you will also come up with this eventually. But this here, I claim that this transition is equivalent, that is my claim, that the possibility of this transition is equivalent to allowing the notion of a map that is of a map generally defined there, a map as a general assignment that can't be described in any other way than assignment, well, actually in set theoretic terms, meaning ordered pairs. But what are ordered pairs? Well, ordered pairs of mathematical objects is just bringing things together just because we brought them together. It's nothing else but that. You could, of course, say, well, but sets are already bringing things together. It may be even in more abstract fashion because we only bring together mathematical objects, not their names. Here, of course, the same, but what I'm trying to say, well, sets is already kind of bringing things together. And you would be right. This does not require a notion of a set. This also does not require a notion of a set, and this does not require a notion of a set. As a concept, this is perfectly fine without a set. Set we have introduced first, and then we introduce maps, but this is just how we formalize things. Actually, set itself is also such an assignment. It is an assignment to certain objects of the property of being comprised of comprising something, of comprising a set name, of comprising a collection, of comprising a naming that will name exactly them. Of course, a set is exactly such an abstract thing, and you could view a set as a map in the sense that it is artificial assignment. So I'm not necessarily talking about maps per se, like we define that. But I'm talking about artificial assignment. As such an artificial assignment, on the level where we are, it can be base phrased in the language of maps. But of course, I'm talking about artificial assignment in general, and set is already involving the notion of artificial assignment. And now, the thing is, this, until here, leads to very primitive maths. I mean, to very primitive maths, well, meaning if you don't know anything but that, then the horizon in which you are encompassed, it's really narrow, right? Right. Maybe you don't know exactly what I'm talking about, but I'm just claiming that. And of course, there are things like number theory that basically deals only with natural numbers. But now imagine number theory would be without any tools that are yet obtained only by the transition to something continuous. Now imagine number theory would only have tools encompassed in this domain. Then the mathematics would be on a very intuitive, immediate level, right? And here's the thing. We said that the transition from the natural world of immediate perception to abstract intelligence happened by means of artificial assignment, namely by creating a language, by creating a medium in which we could create thoughts which allowed us reflection, which allowed us clear formalization of information. That was allowed by the artificial assignment. So the abstract intelligence is based on it. And now compare that with that. The transition from the very nature intuitive maths to maths that is genuinely abstract, meaning not comparable with the real world anymore, is exactly this transition done via artificial assignment. And here I make another claim. It's not just about maps artificial assignment. This, so I claim, is equivalent to axiom of choice. And that is why, and I told you, if you don't know those notions, okay, there will be links in the description. You can read it up if you want, but it's just for those who know. That is why continuum hypothesis is unsolvable. That is basically the hypothesis that there is no set that has, in some certain sense, more elements than natural numbers, but less elements than real numbers. Continuum hypothesis is unsolvable. That is, it can be proved, it can be disproved. And there's a weird thing in mathematics is unsolvability. Because without this transition, and if this transition is equivalent to an axiom of choice, then that means we could have mathematics without anything that goes beyond it, right? So there would not be anything that is not countable. And about countability we will talk, or maybe not in this series, I don't know yet. I hope actually in this series. I'd like to do that, but I don't know what my mood will be. So this is why continuum hypothesis is actually unsolvable. This is my claim also. Claims. Because even the existence of R itself is equivalent to something, so to speak, optional, right? And constructivists, which I'm none of, would even say, well, axiom of choice doesn't work. But well, if it doesn't work, then there are no real numbers, or at least as I see it. But it gets worse. It gets worse because if we are genuinely involved, then it's another claim. Any limiting process. Okay, maybe I should have done this equivalence here, but it doesn't matter because it's all equivalent. So it's not just that you would not have real numbers, you would not have any limits. And this is kind of obvious that this is equivalent to that. Well, because the irrational numbers are dense and the real numbers, of course, I'm thinking about that. But okay, that all is notions that I will link, but I'd like to have this in this video because it's a very important subject that moves me a lot. So you see, the real numbers are really the step or the building stone where the genuinely abstract intelligence comes into play. That point when we abandon the naturality of thought. Of course, mathematics itself kind of abandons it, but um, at least mathematics in this domain is very much in line in everything with how we describe the real world. Not necessarily with the real world itself, but with how we describe it. But here is another step, and this step is a step of another qualitative magnitude, so to speak. And this is magnificent, right? I told you that it is all about mathematics, not necessarily about your world, but what I meant, mathematics mimics our developmental transitions in how it itself is to be developed or has been developed. That is, it mimics the path that our intelligence has taken on some higher, more abstract levels. And this is magnificent. That's why I'm sometimes talking about mathematics being actually a model for everything, not just in the sense that we can model it um, using mathematics, but also in the sense that the essence of mathematics, of mathematical interrelationships, itself mimics the structure of our relationship with the real world. And what do we have from the real world? We have only our structural interrelationship with it. We don't actually have anything else that we can genuinely observe, right? We just extrapolate that there is something else, right? If we are completely honest. And it is reasonable, of course, that to believe that we should assume that there is something else, of course, but I'm not talking about that. I'm just talking about mathematics being a model of it all just by its essence. And this is very remarkable. That so that you understand what remarkable notion that is. It's not just some assignment. It's really the building stone of abstract intelligence, if you wish, or I would like to say of of human intelligence per se, if we go to the very, very beginnings and actually think of what happened there. Those, as I said, that creation of language, that creation of abstract thought, that simplifying out of objects, that was exactly the same what is happening when we introduce in maths a map, or what when we more precisely begin to deal with the concept of the map. That is where mathematics truly began. Mathematics as structural, um, as a structural entity, not just mathematics as proceeding that begin, of course, with Euclid's proofs, but mathematics as structural entity, as structural entity with own existence. That began with sets, with maps, and so on. You can't actually, well, you could say that set is primary, but set is already involving that very thing. Right, as I said, set assigns this state of being named as a set to a certain portion of objects, and that is already, if it is general enough, that's already an assignment. And a map is assignment formalized per se, of course already in language of sets, but nonetheless. like you don't have to understand 100% what I'm talking about, because it's not uh I mean, even exempting those notions that you probably do not necessarily know, because it's not meant to be precise talk. It's such topics where you can't do precise talk. It's not mathematics. It's how the mathematics can be viewed, and this is already on a level that is that evades precision, because it's such relationships that you could describe in a multitude of ways, and you would still only be able to touch them. But okay, that's the beauty that I wanted to show you, that a map is already something highly non-trivial, and that we are able to state that in such a comparably trivial fashion is amazing. That's fascinating. And you see that all maps, all serious maps, is actually built based on maps, because, well, assignment, or more precisely on assignments, because assignment is just such a powerful thing. When you can just say that something is brought together in an artificial way, it is magnificent. It opens such broad horizons. Of course, now, if you are knowledgeable a little bit, you could say, "Oh, but maps can be very natural. There can be like maps that kind of suggest themselves, differentiable maps, continuous maps, things like that." Like, well, yes, but simultaneously not quite, because those properties of maps, we discover them. We discover them a posteriori. They are not there per se before we have defined a map. Of course, one could argue about that in one direction and in the other direction. Um, the general notion of a map is much broader. Those particular examples of maps that arise there, well, you would not see them as maps if you would not have introduced this general notion of a map, and this general notion applies to a much larger spectrum of phenomena, and really everywhere where something interesting going on, this artificial assignment is in the play. And also for the subsequent, keep that in mind, that it is just artificial assignment, so that you kind of get a feel of what is happening when you see dependence on some x, maybe of a real function f of x, and you just see that this is moving somehow here, and those objects also move in a certain way. Well, keep that in mind, that those objects moving and those objects moving according to them is just because we made this assignment so that we can talk about interrelationships. You might not understand yet what I'm talking about, but you see, it might be really helpful if you grasp what I'm talking about. I mean, like some basic essence of it, then it can be really helpful for you, at least in my opinion. Okay, what should I give you links for? I should write it down. Mm, should write it down, otherwise I forget. Links. Okay. Density. And of course, when I'll give those links, it does not necessarily mean that you'll be able to understand what is written there. It's just for completeness, because uh, at some points, for example, here, I'm not sure if it is explained elementarily. Um, I'm intending to give links from Wikipedia, of course, without doing any fancy research. Um, it will be stated probably in abstract mathematical terms, which we have not yet discussed. So that's just for completeness, just to look at it. So don't be afraid or thrown off of that stuff. It's just that um, at some point you'll be able to read what it actually means, but now you can just do a little peek, right? Constructivism. Oh, I forgot to mention an important connection. You see, yeah. There's more, of course. That's one of my favorite parts. You see, axiom of choice is equivalent to Returns lemma, right? And now the thing is, if that is true, really, then that would kind of suggest, and this is already suggested by here, that kind of like allowance for supremum axiom of real numbers, or actually allowance for supremum axiom in a field. Of course, we need ordering, like for supremum axiom in a field. And this is kind of also self-suggestive, so I'm actually pretty certain that I'm right about that. But, well, I don't think it has been proven or addressed yet. Allowance for supremum axiom in a field. Right, in an ordered field, in ordered field with order relations being compatible with the basic operations. But okay, let's not go into it. I just wanted to state it one time because it's just so amazing. This is alternative formulation of this optional thing in mathematics. It kind of talks about maximal elements existing, no matter if you can construct them, no matter if you know how to find them. And this kind of talks about same thing, but at least in case of real numbers, about something natural. Right, and usually it's used in case of real numbers. Okay, axiom of choice. Returns lemma. Supremum axiom. Okay, unsolvability. That's actually quite a lot. But yeah, that's what so that's where the structural wealth of real mathematics comes into picture. It's like after school it all begins. Opinion hypothesis, unsolvability. Well, limiting process is quite simple. You actually like limit of a sequence, for example, most simple thing, limit of a sequence. I don't know, I don't think I need to put a link for that. And anyway, since it's links to Wikipedia, you could just Google it. I mean, just look it up in Wikipedia yourself, but okay. Construction. I know that it's much easier when the links are already there and you have only to click, even though it's just Wikipedia. Construction of numbers. Right. Stretching of. Oh, okay. Combinations up. Okay, so we encountered the notion of a map, and it is just an assignment that takes each element of the domain separately. It assigns to this element unique output. And of course, as always, definition. Instead of domain value space map, we often write. So let's do some maths with maps. We'll start in a second. Instead of x, y, f, we often write. Oh, well, actually, not quite. We will need some definitions, and then after that, there will be theorems. Definitions, maybe also examples. We often write very self-suggestive notation, right? It's just that f is map that is going from x3 domain to the value space y. Alright, and for particular assignments, we just write that, and pay attention, the arrows are different. This is assignment arrow and this is going to arrow. Right. Or for assignment also just f of x, and this is kind of of evaluation, but what we mean just to this x is assigned this y, so we mean exactly this thing, right? Okay, and this just means if it is this y, and it is of course equality, because well, we want to talk about this object, because y now via the introduction of this map becomes also this object, because this is y is the object that is assigned to x, and this is what is assigned to x, and what is assigned to x is equal to y, because we have stated that, right? So this equality is um kind of immediate from the definition of assignment of x to y. You don't have to ponder it, but I just wanted to point it out that you don't have to think that here is some equality that is based on nothing. It is based simply on the assignment itself, right? This mathematical object is this object exactly by assignment. Right. Okay, well, Okay, that took quite a while actually. I've not necessarily expected that, let's be honest. Okay, let's introduce associativity. Definition F. No, let's introduce composition first. I'm too fast. We have not yet introduced composition. So if we have maps like that, well, actually, we don't need to have it like that. It also be something like that. Why do I do that then like that? Well, or more precisely why? Okay, because, yeah, okay, I get it. But then this kind of, okay, this kind of diminishes in generality. So let's do it differently. I reduce that to that. And I could also reduce. Okay, no, it does not. Okay. Okay, that works. Definition. So let those be maps, and of course I'm not writing let be and things like that. We already used to it. So those are the maps. And pay attention, this goes from X to Y, and this goes from Y to Z. Those are maps. Then we define and of course it's again a map. I'm not writing it down. G, and pay attention how we denote that, namely the map. So, but let me write it down. Let pay attention to how we denote that. F, X, Z. So that's of course a map again. We define such a map. But we have not yet defined how it works. But pay attention how we write it. G is here. So G, the map that kind of is coming after meaning that here X to Y, and here we are in Y by going with this map, and we go with G. So this that is coming after, that is actually on the left, right? This is what is coming before, that is on the right. There is a justification for this notation, so it makes sense. We sit in subsequent, and we just define that, right? To define a map, we have to define how this map works. And we already have those maps, right? And to just define, and of course here X and X, we just define it, recall that is definition, that we first apply our map F. So don't be confused by this notation. Here we have just application of our map F to X, right? This gives us some element of Y. Just by definition of the map F. And here, what is happening here? Well, this is a legitimate element of Y. Just written in this funny way because we want you to specify what that is. Well, but to that we can apply G, of course. We can apply G because, well, that is just a legitimate element of Y, and what G does, well, G takes elements of Y and it maps them, so assigns to them, and we call it maps. G assigns to them elements of Z, so this is in total an element of Z. So this assigning to x, and then assigning to what? To what we have assigned to x, another thing, this is a composition. So a composition kind of, well, it's actually very simple. It just, informally, it's just that, right? We go by f, and we assign to that y that is for x, right? And when we have that yx, that is already like given, right? And we just assign to it cyx. And I'm just denoting it. I have not defined this notation with indices, but you understand what it means. That is, this is y for x. Just do not write just y, what is y for x. Here z, y for x. Or just forget the indices. We first do the thing with f. It assigns unique y, because that is how map is defined, our requirement. And for this y, we have it now. We now apply g to this y, it assigns c. Right. Okay. But the formal stuff looks like that. Right. And this is a composition. And well, you can think about how it works. It's not complicated at all. It's just first to do the thing of the one map, then do the thing of the other map. And so we have defined a composition map from this space where we started, and it goes to the space where we finish, right? And it is defined in this way. Well, go to this via f, go from what we obtained via f, via g, to the next. And of course, we could concatenate that z to, I don't know, z to w, and so on, as many f's as we like. Right, definition. Well, actually, not definition, but theorem. But I don't know if it deserves this name. It's very short. Very short proof, but okay. Let's do everything in due order. Theorem. The composition of maps is associative. And we are already masters in associativity. We have seen it all 2 times. So we know what is meant, but if not, well, we'll see in a second. The composition of maps is associative. Okay. What does it mean? Well, it is for maps f from x to y, g from y to z, h from z to w, have, well, what was associativity? That was that we can break it as we like. And of course, customary, we just show it for the case. course, I have already written it wrongly. We should pay attention to how the composition is written. First, the last map. And this gives me a map with the uh, corresponding domain and value space, just like in the definition above, right? And this map that it gives me, I can compose with this map, and these brackets mean I take this map that results from this composition, compose it to this map, and you could check, just think in your mind from where to where it goes, from where to where it goes, that it satisfies our definition of composition. And here we have now I'm taking that map and I'm composing it with that map, and again verify in your mind that it works, or maybe not in your mind if it is too difficult for you, then verify it really, like write it down for yourself. Okay, what's that funny arrow? Okay, well, now we have to prove that this map that results here is the same map as the map here. And well, what is equality of maps? Well, by the way, we have not defined it. We should have defined it. Equality of two maps, but I guess you already know. But I mean, it is self-suggestive, but let's define it properly. Maybe it's not as trivial as I think. I don't know. Definition, equality of maps. Because we actually have not defined when two maps are equal. Equality of maps. Clearly, we can only postulate equality only when the two maps already have exactly same domain and exactly same value space. Right. And also pay attention here that domain and value space we choose. Right. So we could have a map that kind of to us seems to work similarly, like x squared, for example. We could choose very different domains. So the map kind of does the same. We could say that, but a map is different. But the map is different because we have different domains that we could choose and different value spaces. F1, for equality of maps, we have to have that their domain and value space are same. Otherwise, there's no talk about equality at all. Their domains are respectively the same. Their value spaces are respectively the same. That's what I mean. Equality of maps are equal. If for That's how I write for. Of course, I could write the quantifier, but usually when we write a text, we don't use quantifiers, we use just natural language. Or more or less language, no, more or less natural mathematical abbreviations. And with lazy abbreviations. That's what means mathematical in this case. For x in the domain, because what makes a map makes how it maps. And for x in domain, we just have to have that the things that it assigns to respective x are always equal each other. That it assigns and the other map assigns are always equal. That's just that, right? Contemplate the definition for a little bit. Okay, so contemplate it. Okay, let's go back, and we want this equality. You should verify in your mind that we have indeed same domain and same value space, so it makes sense to compare to begin with. And now let's prove it. Now we prove, we just have to verify that for each x in x, that's actually true, that evaluation of this map, and recall it defines really a proper map, and evaluation of this map at x gives the same. Okay, let x be element in x. And by the way, I don't know if I have already mentioned it. If I write let x element in x, then since I don't impose any requirements on x other than that it is element of x, we could just theoretically do it for any element in x. I mean, we could take one element in x, do it for it. We could take another element of x, do it for it, and we could infinitely many times perhaps do it and verify it for each element, but we verify kind of for all elements at once. And this is what means x element of x. Again, pay attention, only structures and structure interrelationships matter in mathematics. So if I don't impose any requirements, then clearly the reasoning would work just for any element, and that is why it works for all elements. If it does, we'll see in a second if it does. Then how proofs like that, we just go by definition. Then first, let's evaluate the left side of the equation, the supposed equation x. What do we get? Well, by definition of composition, this is now a map, this is now a map, and we are composing those two maps. Clearly, here stands the composition of those two maps, of this map and of this map. And what is that? The composition evaluated, well, we have to take this map and we have to evaluate it at what this other map that precedes it gives, right? So what we have is that here. All right. And what is that? Well, now we have this element, right? This is now an element of y. And now we have this map, and we just apply the definition of composition, just the same. We have this map to evaluate this element. Okay, what do we have? Well, of course, it might seem a little intimidating, but no worries. That just means, well, we have that element f of x. We have to evaluate it at g by definition of composition, right? And evaluate it means just assignment. So g assigns to this f of x something. And by definition of composition, we have now to evaluate h at this element that comes out. And here the element that was plugged in into the composition was just this, because we started here and just did the first step, right? So nothing special has happened. All right, I should see that parenthesis matching everything properly, right? Okay, so now look at this. And we'd like to have that this is actually that right side of the supposed equation evaluated at x, right? Now look at this and recall the definition of composition, kind of backwards, but you recall, of course, in sense of structure and data relationships, the equality is just symmetric. So no, I'm too fast. Sorry. I should not do it like that. That confused me in my first years of studying, so I should not do same thing to you. Yeah, by the way, I was a lot of confused in the first years of studying, so it's normal. It's completely normal. Like you just have to internalize the things, and for that you just need practice. You need to think about them. You need to play with them. You need to solve problems. Only that way you really internalize things and like become fluent with them. And you see, because I like to ponder things, I'm just finding things everywhere to ponder. So sometimes not fluent just because I think about too much that one doesn't necessarily have to think about. Okay, well, here, just by definition of the map H, right? We just here have this element g of f of x, because here we use that definition. This is where we arrive. This is exactly the notation of that we have evaluated this h at this element g of f of x. This is exactly where we arrive by definition of composition here, right? Have evaluated that, but this element by definition of composition applied to here, we could rewrite as this element, right? The definition of composition of G composed with F just applied in reverse, kind of, but we call structures mathematics that are connected by equality asymmetric, so there's no in reverse. It's just that our mind in the beginning is used to think maybe in only one direction, but it's really it's really there's no in reverse. It's just equal, and that's it. All right, we get that. Like replaced equal thing by equal thing, got equal thing, of course. Thing is consistent. Okay. Now this is an element, and h is evaluated at this element, right? Now we apply the definition of composition of h and g composed with f. So two maps, h, g composed with f, and obtain the desired It can be that you are struggling by some steps here. It's normal because you have to let it sink into your mind properly. So don't let it irritate you. It's completely normal if it is the case. Just write it down yourself. Start your thing hard, how we proceed, like cover what I have written and things like that. And just look at that, try to do it yourself, and then that will work for you. Right, eventually. Okay. So if you're struggling, it's normal. That's the message. Okay, well, we have now had associativity of maps. And you might be wondering, well, isn't that nice that the maps are also commutative? Like something by sets was commutative, like intersection and union. Something from which we had that by sets in logical statements was commutative. Why not also maps? Sadly, that's not the case in general. And for that, well, let's consider, I don't know, question. Is composition perhaps commutative? And of course, composition of maps, we mean here. Okay, most simple example would be to give you matrices, but since we haven't talked about matrices yet, I won't do that. I will construct a simpler example. Composition perhaps also commutative? And the answer is no. Consider something simple. I don't know yet how I'd like to define them, but let's just state that they go from the nature numbers to the nature numbers, so we certainly can compose, right? And don't be irritated here, these sets look different in the sense that I used different letters, but here sets are the same. Well, different letters in mathematics does not necessarily mean that it is different objects. If I'm stating something general like let this be mapped from there to there, let this be mapped from there to there, and of course all the letters, actually all the sets could be the same unless it's explicitly stated otherwise. All right, so I can certainly compose them, and let's say, well, I don't know. Mm, yeah, very simple. Just F maps every natural number to this natural number increased by 1. So it increases each natural number by 1, and G maps. And you see, this is now not abstract maps, but really like down to earth maps. They do familiar things, they do like things at school, only that they do it not on real numbers, they do such things on nature numbers exclusively. Could have also considered real numbers, but just what I came up with. Okay, those are not commutative. And of course, as you can think, if you think hard, you will realize that if we have found at least one example for which our claim does not work, the claim is in general not true. So it is not, when we ask, is composition perhaps also commutative? That would mean always commutative. So what we are actually asking in mathematical language, what we're asking in natural language, is composition perhaps also always commutative? Because associativity was like always given, right? For maps that we can compose it that way, of course, but this is just what is self-explanatory. Otherwise, the situation for the question wouldn't be there. Is composition perhaps also always commutative? And indeed, here we have a counterexample, and one counterexample, of course, already disproves the always part. And then there might be some that are commutative. Of course, there are commutative maps. For instance, take same map, like take same map, and well, of course this is commutative because we are doing same thing, right? Take G 2 times, for instance, something G composed with G, I mean, cool, can do, why not, can do, that is legitimate map, we compose it with G, can do. Those are not commutative. For instance, no, it suffices to find at least one element of n for which we map it to different things, and we just take 0, right? For instance, and we apply the maps respectively. That is for instance. Okay. F G applied to 0. Well, the definition of composition is just G applied to 0 and F applied to the result. G applied to 0 is just, well, 2 multiplied by 0 is 0, and F applied to it is just 1, right? If you could not follow it through, then just write it down properly. And this is not equal to what? Well, G composed with F. G composed with F, first F, then not equal to 2. And you can realize that this is G composed with F applied to 0. I have done it in my mind, but let's look at it properly. F applied to 0, well, we add 1. This is 0 plus 1 is 1. And then we apply G to the result, so to 1. And G applied to 1 is just multiplied. 1 multiplied by 2 is 2. Well, okay, verified, and this is it. So maps are in general not commutative, and you could wonder, oh, maybe it was specially chosen maps. Well, very seldom in mathematics by such general questions you would even think that, but it's like not customary to think that if you found a counterexample, that's fine. But okay, by numbers, it could be that you found a counterexample, but nonetheless, the formula works afterwards. So let's address it for a little. You can think really easily that there are like lots of counterexamples in all different settings, probably for almost from every set to every set, unless there's only one map. I'm not saying it exactly, but I guess you can find counterexamples. I wouldn't think about that if it is constructive or not, but I mean, if I would think how to construct it in general, but yeah, it's not a particular case, but this case just illustrates that um, that situation, that it is not always commutative. Okay, and as I said, a counterexample in general disproves the general conjecture, and this is very logical. You can think about it. Also very logical, like in natural sense. Okay, well, what is left to do by maps? Oh, actually, not a little. Okay, let's define image and pre-image of a map. Definition: F is of course a map. If it goes from X to Y, well, we don't have this notation for anything else, so it is a map. That is X, not assignment. Definition from F from X to Y. The image of F denoted in a self-suggestive way of F let's do it differently. Let's do it more generally. The image of F. No, the image of a subset A of X, and of course that means any subset of any subset A of X under F is, and that is a definition. No, I didn't like that. Just F kind of evaluated at A, but of course it's not evaluated at A. If we have something funny like that, well, probably it means pointwise, and of course it's a set. And what I mean by pointwise, well, just the elements assigned to elements in A in sense of a set. So the set of all elements that we can meet if we start at A and go with our F. Right? All right. And then we have the pre-image that is kind of going in reverse. That is, we are going from a subset of Y. And what does that mean? Well, we just take the elements at which we could have started to end up using F in the certain sets that we consider. The pre-image of a subset, and of course it means any of a subset B of Y and F is, and that we denote just like that. F of minus 1 of B is defined, well, as I told you, that just all elements which we could have taken to end up, and of course, f of x is clearly because f goes from there to there, so it is in y, but we could have written that, of course, for clarity, but here we have to write x, oh, okay, here it is again clear actually, but okay, let's write it. F of x is in B. So that's exactly the elements of x that we could have taken to go via F, via assignment to those elements to end up in B. All right. Now we have another definitions. Definition. No, let's have first. Let's have first a lemma about the properties of images and preimages. And unfortunately, as you know, I'm doing this thing with videos spontaneously, so I don't know if I recall exactly what properties actually work. Well, we'll see in a minute. I think I do. Lemma. Um, okay. Let's write it for once let f x y b. Oh, that's an arrow again. Be a map. Then for A, B, element, subset, not element, of course, if it's big letters, then probably subset, at least in our settings. Subset of Y have Okay, so the preimage of the union of the sets, of course they are subsets of Y, right? Because that's preimage. Kind of is compatible in sense of such kind of distributivity, but of course it's not distributivity in the usual sense, but kind of, if you just look at it as formal operations, then you could think of it like that. Compatible with the union. Also compatible with intersection. What else do we have? Well, maybe let's leave it like that. Maybe let's leave it like that. Okay, let's prove it. Let's leave it like that for now, and other things, when I come up with other things, we will prove them in other limits. Proof. Well, we have to show the equality of two sets, right? That is our customary procedure. Is just to take element in one, show that it is an error, and take element in the error, show that it is in one, meaning arbitrary elements respectively. So let x element f minus 1 a okay, I started to prove another thing. And what does it mean? Well, just by definition of the preimage, that means just that that is an x that lends via f in a intersect A's union B. All right. And what do we have to prove? We have to prove that well, if f of x is a, or it is in B, right? And we have to prove that actually f of x is in A or it is in B. But okay, let's do it formally. And okay, you should immediately see it. You see f of x is in the union of A and B. So it is in A, or in B, or in both. And then that is f of x is, you could choose is in A or in B because it is symmetric. If it is in A, well, then it is in here. This in B, then it is in here. So in total it is in here. When it is in both, it is in particular. But let's do it like really cleanly. Maybe it will be only confusing, but it is actually more cleanly than just to say, well, it is in here. We see it that immediately, of course, but okay. Then let's what I'm doing now, it's not necessary. If you see already that it works, well, that's fine, because it's very clear, right? Or could we do it differently? Well, this element of A union B, then okay, yeah, I can do it for you in a video self-suggestive way. Uh, hmm. That's actually interesting to think about how to do it in a more self-suggestive way. Okay, and then hmm, what would I like to do? F of x is element of hmm. Okay, now let me see how to do that like that. It's okay. You see, I'm not really. It's not necessarily at all what I'm doing, what I'm thinking about. It's just that I'm trying to do that as plausible for you as possible. But if you just think about it logically, well, we have f of x is element of A union B, and that is just by definition of a union, or maybe yeah, best would be we use really the definition of a union. So that is self-suggestive enough. f of x. That is actually the very right way. Of course, no one actually would do that, but let's do that. F of x is element of, that's just by definition of a union, right? And I wanted to do now an argument that is based on that, but that's even better. So then we have that, right? Just by definition of a union, if f of x is element union A union B, then we actually have that. Right. But this means exactly, that means, right, just by definition of a preimage. So, and that is just equivalent to, that's actually nice. I never did it in such um, detailed fashion, right? Just by definition of a union again. But you see, that's actually interesting to see some certain dynamics of thinking. You see, we could have said immediately, well, that's clear, right? And how would we have seen that then? Oh, that is, our mind internalized already the application of this logical things, and we immediately see that it works even without uh, doing it in the explicit way. And this is how things very often work in mathematics. On higher levels, you just see that things work, and you know you could write them down, but you don't because you could do it anytime. And of course, the line between like not being able to and between like being able to but not doing, that line might be blurry and there might be problems with that, but generally it works in mathematics, but well, after you acquire some certain degree of mathematical intuition. Right. So you see, for me, it was much easier to see that immediately, maybe for you too, than to write it down explicitly because just you're not thinking anymore in these terms because it makes you slower. Makes you slower because you would have to pursue all those interconnections, and it is not necessary because you just see how it works. Right, it took me a while to like come up with how it is done properly step by step because it's not how it's done, and that's the reason, or one of the reasons for the phenomenon of university professors that just don't see that it is not elementary, that something is not elementary because they are already that immersed in that, that to them 10 steps are one step because they see it. So it's completely normal. With time, it becomes like that. There's no way. We have only shown one direction. So we are not yet by two. But now you can say, well, we have to start by here and we have to go back. And of course, what we do, well, that was equivalence. That was equivalence, right? Because that is exactly equivalent to this. This is just the definition of that, right? And having that, well, of course, this is by definition just this. So here Again, implication works also in the other direction because it is equivalence, and here true, so we are really done. Since all implications, if you don't believe me, write it down and you'll see what I mean. I mean, if you couldn't see how it works. Since all implications were actually equivalences, we are done. Alright, that was one. And so we have proved immediately also the other direction. Let's do two. Well, let x then have, well, and let me do it like quick because it's all same arguments basically. And that's if and only if, because there's just definition of that. Right, just like there. Here again, definition. Okay, what did I write? Here again, definition of the preimages. Right, and with that we are done. So that finishes the proof. Okay, that's right. Oh, I see that my board is hanging a lot because there's a lot on it already. So I should separate such considerations into different boards. Okay. Okay, well, what do we have next? No remark. You might wonder about So let's just take another set of operations and maybe it works too. And let's take, of course, well, first that, because we had that match with preimages, right? It doesn't work, of course. Well, I mean, it doesn't work, but we have first to think if we can see that it doesn't work. Then we had that match with images, but nothing with images. Maybe also. Okay, let's try to think about it. Well, let's first discuss those ones. If we have A union B, then why wouldn't that be that? Seemingly, that should work. Why not? Like we have A, we have B, and that F maps into something, and that seems to work. Okay, let me think. If we have um, more precisely, maybe let me think why it does not work. Because I don't think it does, but I'm not sure if I see why. Because actually it should work. It should work. Because like we are doing nothing really. And while we are at it, by the way, also maybe this one works. Mm-hmm. Let's think about it. Well, So this one works indeed. Okay, that will prove in a second. What about this one? Well, I think I already know that it does not work. Why exactly? That's simple. You see, let's say we have such a map. We don't need to give a concrete example because it will be clear, but it is really easy to give one. You could think about it if you like, after you have seen what I'm about to do. Let's say we have here like those 2 points, and those are distinct points in some set, right? And they are mapped by our map. And you could just take a set consisting of 2 points. And they are mapped to one single point. And what we have here, well, intersection of those is of course the empty set, because it's two distinct points. So the set that contains simultaneously a point that is simultaneously this point and this point, of course empty, because 3 points are assumed to be distinct, right? And this, if this map maps this point to this point and this point to the same point, then the image of this set consisting of this point would be this point, and the image of this point would be the same point, and then the intersection would be the same point. It would be non-empty. So this would be an empty set, and f of empty set, well, we don't have anything to map to, so that's an empty set. And this, of course, like definition, which we have not stated, but which we have not stated, but which is kind of self-suggesting. And we could say, well, that is not defined while this is a proper set. So that is, of course, not true. Now let's think about this one. We have A without B, and we'd like to have F minus A without F minus 1A without F minus 1B. Okay. Let's see if it works. Well, I think it doesn't. But let's just think about it. I think we could use same trick. F minus 1. Similar trick. We could use similar trick. Maybe kind of in other direction. Let's see. Um, I'm just thinking about how to come up with an example. And that would not work. That would not work. Because you would have just empty and you would have just some set. Okay. How that would work, of course, but so what we are trying to achieve is to have that empty. Right, okay, let's say that this is that, and this should be not empty. And yeah, that's simple. Okay. Let's say we have a situation, and again, you can just think of an example yourself. You just take basically sets with any elements that you like, maybe numbers, maybe something, and you just define your map explicitly. Since it's finitely many elements, there's no problem with that, right? All right, you do the following thing. You just say, well, let's say A without B would be that one without that one, right? And now the preimages should be so that it doesn't work. And then we could just say that one without that one would be left with that one. And that will give you that. But now this would give you this, right? So if we would have, if we were to take this and this, then it would work. Okay. So let's say we have this one, this two. We have this two. And we take one away. And we just do the following. We say that those three. No, we have to have right. That might actually work, but I'm not sure yet. It might work. So we take this to this, and we take this one to this one, and we take, well, if we take this one from this one away, and the thing is that they are kind of independent, right? Seemingly they are. This might actually work. Let me take a look at it. Mhm. Yes, that seems to work. We'll prove it in a second too. All right, that was kind of surprising for me. I didn't think that this actually works. I have forgotten that. So you see, to forget such things is normal because you could prove him anytime or you could look him up. Oh, okay. Some people would keep all of this in mind, not necessarily all of them. There are people who are really like forgetful in that regard. So that's not necessarily uh, it's not necessarily a big disaster when you forget something like this because there are like tons of identities like this. Right, and this of course doesn't work, so the image kind of behaves nastier. Nastier than the pre-image. That you could say by simply considering again that one. You see A without B. If we take that without that, well, we have to exclude something that is already not here, so we just have f of A. So we have this point. But f of A without f of B, since they map to the same thing, well, f of A without f of B is empty set, and this is not equal a set consisting of one point. So we have established, or I have seen that those two are true, so let's prove them. And that's another lemma. Okay, again, F is a map from X to Y. Okay, what do we have? We have a B subset of X. And we have C GC subset of Y. I just used now different things than A and B because here A, B will in Y, here A, B will in X. Maybe it's a little bit confusing, so let's do it properly. Then, now, what do we have? 1, F minus 1 of A without B is equal F minus 1 of A without F minus 1 of B. In particular, so of course you recall that complement was just a special case of taking away a set from the large set, right? And what is large set there? Of course, Y. Okay, so let's write it like in complement fashion. And you can then decipher that for you. Decipher or decipher? I think decipher. You can decipher it for you if you like. Well, like A was an so we said that those are D and C, right? A and B were in X, but we are applying the F minus 1. So of course we are currently in Y. So let's take D and C. You can just double the pace of the video. If it goes too slow, then it works exactly normal. Okay, well, D, C. And now we are interested in that, and that is of course in just what F minus D complement. Right? Because D complement is just Y without D, then we apply that, and we have a minus 1 of Y, which is of course X. You can check it for yourself. And then you have without with minus 1 D, and that is complement X, right? All right, then 2. F of A union B is equal to F of A union f of b. All right, let's check that. Now, first check that. Let x. Oh no, let's call it. Yes, x, because we are considering that. Right. F minus 1. D, C. Right. Then have. Oh, what do we have then? Let's just check that. And just take a look at that. This is equivalent to x and f of x and the without c, right? Which is how it works. The definition of the preimage of g without c, then that is equivalent just to the definition of the set theoretic difference f of x. And you can see that we already applied those set operations fluently, just like we applied by sets those operations with statements fluently. It's just how it works, right? F of x, no element, which is exactly the negation of being an element, right? That is, this is defined as being the negation of a statement that this is an element, right? But this is just by definition of respective preimages equivalent to x element f minus 1 of the and simultaneously x, of course, no element of f minus 1 of c. You could also see it by equivalence via contraposition. So you just take those two, recall the contraposition lemma, and then just recall that f of x element c is equivalent to x element f minus 1 of c, right? And then you have equivalence there and use contraposition on both implications, right? We recall equivalence is equivalent to implications, and implication by contraposition is equivalent to the implication in other direction where these statements are negated, right? Okay. That was quick, and it was intended to be quick because you have to be fluent with that already. Of course, if you are not, it's not a big problem. You just have to practice, but yeah, I won't go into the detail on that. Yeah, it is trivial, so there is nothing in it. Just, it is not trivial for you because you have to get used to it. And of course, here again, I just use the definition of set theoretic difference, and that's it. Okay, so we have then proved one, and as I said, that with the complement, I have explained it in words. It's really simple. It's just application of that. And by the way, this lemma C I used really extensively and self-explanatory in the subsequent, higher mathematics. So you should really internalize them too. But actually, everything what you encounter in mathematics, you should like internalize in the sense that you can use it very properly and intuitively. You can forget things, but then, well, be able to recover them somehow and be able, like, not to be astonished, um, astonished structurally when it turns out. So that something is true. Not be astonished in your action. You are allowed to be astonished in your emotions, but not in your actions. When something that you should know turns out to be true. Let X elements have union B, right? Then have let's not call it X. Let's call it Y, of course, because we are in Y, so customarily called Y. Then have, well, just using definitions again. So you see, the proofs for now are all in terms of actual immediate application of definition. So I don't think we even. Okay, yeah, okay. We applied some lemmas on mathematical statements, but it kind of doesn't count because they do not count as mathematical objects. They are like very, very basic building blocks of the very first layer of structure. Then have, but yeah, okay, we already had some abstraction going on, but like very self-suggestive abstraction. We have not applied any more or less abstract lemmas, other than by De Morgan proofs. Here we have had it a little, and have um, by De Morgan proof the general opposites, right? Y element f of a means, well, what does it mean? Here, don't be afraid of the existence thing. It just means there is an X such that, and I'm too lazy to write it in words, so I write it with the existence thing. There is an X. Oh, of course, not just in X, but in A union B, right? That is just the definition of this what of this image of definition of the image of that set, definition of the operation of the image applied to the set, right? Such that f of x, so such that y is the element that is this assigned, right? And well, of course, by taking such an x, there might be multiples, but by taking such one, we can write that certainly there exists. Okay, oh, and I have to continue to write it like that, right? X. Oh, well, how should I write it? Well, okay, well, that is a little bit formula loaded, but you understand what I mean. It doesn't matter how you write it, it only matters what is the year, right? X element A I'm just writing. So imagine we have found such an x, and for this x we following holds, and I'm just writing existence because we have found such an x, but we have not specified, well, let that be x. So again, existence. We just have taken such an x. That means nothing else but that. And f of x is equal y. Right, just because this now holds, I can just say, well, that holds and that holds, or that holds and that holds, because I can rewrite this as x an element in A or x element in B, and then I use the distributive law because this is kind of and this holds, right? Because this is given and this holds for this x, so and this holds. But okay, it's a little bit formula loaded, but nothing special is going on, right? You could rewrite it in simple terms, but if you want to be pretty consistent and like not leave anything not written down properly, then actually what you would write would be this. So again, it might seem confusing, but in the long term, you'll see that this is actually helping because I'm writing exactly how it is done without missing out steps. Well, only like logical steps that I mediate, like x element A is same as x element A or x element B, right? All right. And well, there exists such an x such that, and what is that? Well, x element A and f of x is in y. What is that? Well, that's nothing but just by definition, and this and is just, well, that is because of the existence. Actually, we could have just taken such x and we would have seen, oh, for this x tilde f of x tilde is equal to y, and x tilde is in A, or x tilde is in B, and f of x tilde is equal to y, but we have written it like that, so that's why there is this end, but actually that's just definition of x f minus 1. Oh, sorry. We have another way around, so f of a. Right? Exists in x, and for this fixed x, we'll look at that, and for this x, and for this x, we look at that, and we just rewrite this statement inside of it, and this statement rewritten means, of course, well, x in A and f of x is equal to y, and of course not x, but y. Okay. If I want to be exact, then of course this is not because here x would be missing, right? So I have to write actually. Okay, now I'm regretting that I am that precise because I have to write that because otherwise there would be no equivalence, right? Because otherwise this piece of information would be lost. There would be no equivalence. You might not exactly understand what I mean, but yeah, okay. Doesn't matter much, but just think about it when a little bit more mathematically mature. You see, in time, you will see how helpful those things are that they actually do. and that you hardly find anywhere actually. Right, okay. And what did we want actually? Well, how there exists X element X such that this is true or this is true. Well, and that means what in particular, since truth of that statement means in particular the truth of that. But okay, again, uh, okay, I actually should, if I want to stay precise, then I should think how we get from that to that. Because that's not obvious now. Well, yeah, exists X in X such that Y element f of A. Okay, there's actually no connection first. Okay, that's not exactly equivalent because I have that. Okay. So that's actually a redundant piece of information. Okay. Okay, I shouldn't have been that precise, but okay, if we are already there, just add here that piece because otherwise we are missing out. There exists an X element X such that Y element f of A and X element A. And here add space of information too. Okay, now I'm confusing myself, but here in this bracket we have this piece of information, right? And well, what did we wanted to prove? Well, we wanted to prove that y is actually in the union of f of A and f of B. Okay, so there exists an X element X such that this is true or this is true. And now we'd like to have that this is equivalent to this. Okay, then let's just look at that. Let's just look at that. Let's say there exists such X such that this or this is true. Then this or this is okay. There exists such X Okay, I think I have fixed this problem at least a little bit. Okay, there exists such X that this or this is true, and we'd like to have that there exists such X that f of that y is equal to f of x such that x is in A. right? Right. Actually, okay. Haha. Okay. Well, it is true that we get that piece of information. We get this piece of information for x. There exists x element x such that this or this is true. All right. And this or this is true means, well, or means one of those things should be true. That is the case when that is valid. And, well, and again, think of some fixed x. And now reshuffle that a little bit. How do we reshuffle that? Well, we first take that out. But, well, what I'm doing here is you don't need to do that. I thought in the beginning it would be helpful, but it's actually not. It's only confusing. I'll show you in a minute a version where it's done properly. I thought that it would be helpful to do it in our generality, but in this case, it's actually not. But since we are here, let's finish that. Okay. Well, and here we have first taken out this, right? And then we have that this or that remaining, right? We have distributivity law applied to this statement, and this is a statement itself, and this is a statement itself. So we can take those two statements and can apply, I mean, those two statements in this parenthesis, those two statements in this parenthesis, and we can apply this or, right? Apply distributivity law, this, those. All right. And then what we are left doing is applying this end to the or of those two statements, right? That's exactly how distributivity law works. All right. And, well, we now apply or, and applying or gives us what? Well, again, we apply distributivity law, but now we have four components because it's four different statements. And if we have those four components and apply distributivity law, well, we take this statement, we apply distributivity law like this, right? So what results is and apply, and I already applied distributivity law at the inside. So it's good. It's good that we do that because that way you get some practice And of course, I can already take that or inside that, right? All right. And if you don't see that, just do some practice with statements. I mean, do really write it out. That is actually a good opportunity to practice in that regard. Okay, then I applied that to that, and I have that. Okay, well, I applied that to that, and I wanted to have, well, if I have that viewed through the prism of distributivity law, then I have here this big statement, and I have here and, and I have here this big statement that I apply this to or, and here I have an and, right? I have and I have x. And you see here I already can't explain very much in detail what I'm doing, because it would be just too much talking. I would have to explain to you that kind of I'm taking this and I seeing this as a big statement, and here are two statements inside, so this one statement with this operation is applying distributivity law to this, but applying distributivity law to this, I have to apply this to this big statement, I have to apply this to this big statement, and I have to connect it by and each application of that to this big statement with or is itself applying distributivity law here, and so on. You see, but you probably could follow that, so it's already something. Okay, that already looks good. That's okay, we'll see. And here we are doing what? Well, we are applying distributivity law like this to this big statement. And that is, we have to connect it by an and. But where is the or application? The or application is here, right? All right. And we have that big and we have that now as part of this application, and we have now this big application of and here, and we have now this or, which we have now written out in the ends. Right, so this is a statement, right? This is a statement, and we have to take also this. All right. And now finally we are applying this and with this or. I mean, we are applying or, and we have applied this to this big statement, right? So we have that or inside of this. So we have in total, and we have and inside of this, right? All right, so we have or here. All right. And we have then or we have that to connect that by end. And we have x element All right, that's a bunch of ends. Right, this is really equivalent because we have used the distributivity law, and you can kind of see how we use that. We first use distributivity law by this one statement and this big statements, right? We have taken it out and we got a big or between those two, right? But then for this big or, we could have applied this statement, right? This statement we have taken as big statement and we have applied that. So we have to apply or to this statement, right? Or like this, or like this, and then to connect it by end, right? And then or inside of this is just applied like that, and then to connect it by end here like that, and then here or here or here or here or, right? Now, oh, I don't know if I want to finish that because it's like, it's a lot. Okay, what do we have here? We have y element f of a or x element b and okay, the ends mean that that all is valid at once. All right, x element a e b is no problem, that we have also here. Right, here is an x. Okay, here is an x such that f of x is equal y. That's good. That is one valid thing. That's another valid thing. So that is actually the things that we'd like to have valid. And then we have a lot of ballast. But this ballast is just, well, x element a or x element f of b or blah blah blah. And what we like to have that this is equivalent to let's put it like that. I'm already getting tired of getting that right. As I said, you don't need that. I will show you in a second the version where it is done reasonably and not with all those manipulations. We'd like to have the existing x. We'd actually like, yes. Oh no. We'd like to have just that. And I want to have equivalence. Implication we can have very easily, but I'd like to, to have it all with equivalences that I'm sure that it goes. I mean, that it goes completely formally like done here, even though there was no need. But yeah, that's the interesting part. That's a truly interesting part to get it in exact form or fashion and to get it in exact way like I want to have it. So as I told you, there's no real need. Okay, well, we wanted to have, actually only that. No, ha ha ha. We have written it in such a way that we are bound to write it in a quite weird fashion. Okay, I mean in fashion where it is written down more explicitly. Okay, such that x as element a b and f of x equal y. That's what we want to. Oh, actually, no. Oh, what we want to have is. Okay, yes, now I'm positively tired. What we want to have is the following. We want to have that there exists such an x for which the following is true. Oh, no, it's not what we want to have. If I want to have it in that fashion, then I'm actually bound to write something else. Well, okay, I could write, of course, there exists such an x clearly. I could write it like that, but let's write it a little bit differently. Just to shorten it a little bit, it doesn't change anything. There exists. We started with our y, right? And you want to have that y as element of a of f of a f of b. Right. There exists such an x element a such that f of x is equal y, or exists such x and b such that f of x is equal y. Right. And now, theoretically, we would have to prove equivalence of this monster to this. How did we actually come up with that? This x, so the exists x element x equivalent to such that x is element of a and okay, I have written that out and I have written that out. Okay, there exists x element x such that simultaneously that is the case. Okay, well, maybe it is a formal way, but maybe it is a wrong formal way in the sense that it is a lot to think about. Where there's no need to. See, actually, we are doing trivial thing. And I want you to understand that this is just me complicating things because I want it to have it that way. I want it to do it on that path. But there is nothing in it. These considerations they are evolving about trivial things actually. But as I told you, I will show you the short version, of course. Right, but now let me finish it. There exists x element x such that and so what we have to show that this is equivalent to this. That is, we have to show the two implications, right? Okay, so that is already given. And we have to extract from that x element a. And since that is end, we have that is true. So X element A would be the case, or that would be the case. Okay. And since that is true, that is connected via ends, right? So generally, necessarily, since that is true, there exists an X element A such that X is element A B and simultaneously f of X is equal Y. Okay, now let's play the first two. Well, just think about it. We had a similar case in the proof of De Morgan, where we have just to think that this actually implies this, right? And what does that mean? Well, that means the validity of a statement. There exists X element A or there exists X element B. And now we have a statement that reads as f of X is equal, there exists X element X such that f of X is equal to Y and such that simultaneously X element A union B, which is the same as simultaneously X element A or X element B. And those statements are valid because those are connected by ends, so all those have to be valid. All right, then to have the implication, we just have to assume that this is the truth, right? And we just have to show if look if that is satisfied. Well, if that is satisfied, then in f of x is equal to y and x is in this or x is in this, we just take this one x that is given and we have that it exists such an x, namely this one, this or this is true depending on whether x is in A or in B, or it could be both. Well, then this is valid nonetheless because then just both are valid, right? So this existence quantifier actually doesn't say then anything. We could just fix our x and go this direction, right? And that would be just same x in this existence, same x in this existence. We only have to have existence, so no problem. Okay, then go the other way around. And the other way around, uh, we have here a lot, right? But if you think about it, what we have to establish here is the truth of 1, 2, 3, 4, 5 statements, right? And we have that here. All right, we have that statement that is that or that is true. So let's just take one of them because it's symmetric, and let's establish all others from that. Okay, so we take one of them, f of x equal y. Then the truth of this is established. Okay. There is established that x element x exists with one property first. The property f of x is equal y because we just take this x. All right. Then y element f of a or f of b. Well, if f of x is equal to y and x element a, then that implies that, just by definition of f of a, that implies that y is element of f of a, and that is y is certainly element of this. So this is also established. So this same x has this property. Because recall, we just fixed that x and we're just looking at this x and trying to establish that this x would satisfy this existence statement, right? Now x element A or y element f of B. Well, x element A is satisfied, so we are fine. All right. Now y element f of A or x element B. Well, x element B doesn't fit, but we don't care because y is element f of A based on that. We have had that already here, but let's have it another time. Look at that another time. So this is true. And finally, have to establish the truth of x element A union B. Well, x is an A, so this is established. And this is indeed established. All right. So we have proved that. I know I have made it like 100 times more complicated than needed, But this is good because we got some gymnastics, but let's do proper proof. Uh, and you also see why we had to do that. I wanted to point one simple thing. I just wanted that. No reason in that at all. Uh, let, let's do it like human beings. Let's do it like human beings. But you see, also in that very complicated way, of course, it worked because we have diligently done everything in the right fashion. But let's do it really like human beings. And by the way, this is also a good experience for you because some professors, most of them actually not, these math professors, my university are very, very decent, but some professors do that thing. So you can experience that. It is possible. There are people who do that. I'm not the only one. So let's do it like human beings. We had y element f. Yeah, that this is finished, well, because this is simply equivalent to y, I mean, yeah, exactly. This equivalent to y element f of a, and this equivalent to y element f of b. So if you take the this equivalence is that you take this or, and then you remember the definition of a union that it is given via or, then y is element of f of a union f of b. But let's do it like human beings. Let just double the pace of the video if it goes too slow. I know it's a bad choice with the board now to continue it on and on, but yeah. Okay, well, let y element. Yeah, you'll probably be angry when you see what I wanted to avoid and why I had to go through all of that to avoid that. I didn't expect that it will be that like that technical, but yeah, okay. Like it's really simple. Well, using it. Y element F, then so we start saying that then just by definition of this set exists x and say v such that f of x is equal to y, right? That was just the definition of this image of a b, and we had it in above too. And now the thing that I wanted to avoid, I didn't want to specify, but let x to the be one such x, which is legitimate, it exists, so there will be one such x, and we just are satisfied with taking it and looking at it. Because we can do that and we see what comes out. That be such x. The one whose existence is ascertained by the existent quantifier. And I just wanted at all costs to avoid this specification to let be such x because I never did that and I wanted to see how it works in and wow, it works, but you saw what a detour that was and now you can compare that to this proof and you'll be I don't know what you will take from it. So I just wanted to avoid this specification like let be, why should I do that? Work with existence immediately. Okay, let X tilde be such X, then of course it is such X chosen like this. Y and simultaneously X. Oh, let's write in proper language of logical statements. Right? We have just chosen this X like that. That is just using the distributive law. And instead of equivalence, I just write that is because I have built a sentence that way. But yeah, after that above, you'll be a master of distributive law, I think. Because that was like really challenging. Well, in my opinion, kind of technical, meaning that challenging. Well, okay. R. So here distributive law is really nothing. Right? So it had some good. All right. The X element B. That is closing parenthesis. Right. And then, of course, that is simply equivalent to, well, X. Of X tilde is equal to Y and Y element of F of A. Or, oh well, haha. That is actually taken as same way. Oh, I thought that this would be kind of different because here we have again, we have that this is properly Oh well. Okay. So, this would take us same way, of course, because we have again those three statements, and would again have to apply the distributivity law. So let's just do it really like human beings. It's not because of the existence statement. It's because at that point I wanted to have equivalence at all costs. So it's actually both. I wanted to keep the existence quantifier and I wanted to have equivalence. So I wanted to do it my way. Right? But let's do it normally. Okay, that's too slow. Let me finish it and I should start a new board because it's just too slow. I mean, yeah, that will already finish the video because it's just getting too slow. And I'm not sure if a new board will recover immediately. Okay, let's say that has been erased. And we just say, well, that implies, because that's certainly true. That just implies, well, y is element of f of a, or y is element f of b. Hmm, I'm actually starting to doubt that, if that is really true. That is of course experiment. Or it would not make much sense. Right. Of course, it's like, seems to be obvious, right? But okay, we have to check buff and okay, oh, wait. What am I doing? Uh, this, we know that this implies this. Right? We know that this implies this. Okay. Yes, I see that. But okay, let's check it for completeness. Oh, let's say that is true or that is true. If that is true, then that implies truth of that. What I'm trying to say, the implication is certainly valid because if such I.II.I exists, I mean, if that is true for the I.II.I, right, then that is certainly valid, right? So the implication is valid. And so if that is true, then that is for sure true. And we have a choice. One of those should be true. At least one of those is true. If at least one of those is true, and this implies this implies this, of course, at least one of those is also true, because via truth of this, one of this is also true. All right. All right. And now let we just prove the other way around, right? just proving both subset relations instead of doing crazy things. Let that is the symbol for proving the other way around. Could also have written the subset relation, so that we are proving the subset relation the other way around, but we know that they are nothing by definition, so let's do that. Let y and f p, that is exactly t of p or y element f of b. Right. But then we have what? Well, no, that we already had. Exists x element a such that f of x not we are talking about y, we are talking about x giving y certain property, and since we are talking about equals to y, right? Or exists x element b f of x. Equal to y, right? But well, if that is the case, and that is equivalent, and that's in bracket, right? I mean the parentheses. We have already seen something like that, right? f of x, y. Oh, let's don't take necessarily equivalent, we only need one direction. But of course we could also do equivalent, but don't need that. F of x equal y, and here exists. No, let's say Okay, let's state already this. That implies because that indeed does. X in A union B, f of x equal to y. And why is that? Well, one of those is true, right? And if one of those is true, well, just fix that some x that does that. For this x, we have f of x equal to y, and then this x satisfies this, right? So that works, and this is equivalent, and we send it immediately in equivalence. But we would also be satisfied with implication, right? Why not write it? Why? Okay, no, implication because yeah, equivalence because it's just existence. It's not a chosen x, right? Right, and this is indeed equivalent to that. Right, so you see, there was also an easy way. We have heroically mastered the complicated one. And of course, there was also a way to see that like immediately because that's also how I have seen that in mind. Because you see, just let this be like this, then such an x exists, and f of x equal y for some x in A union B, but then like this x, if it is in A union B, then it is in A or it is in B, and simultaneously it is f of x equal to y, which means, well, uh, either one or both is true, but x is certainly in A or in B, so y is certainly in f of A or f of B. I mean, not at that point, but here. Uh, so that's one direction, and another direction is quite similar. So it is in here or in here. So f of x is equal y for in x. I mean, f of x is in here or in here, but it means we have x in A such that f of x is equal y, or we have x in B such that f of x is equal y, and that means if we have x in A or in B, then it is certainly in here, and f of x equal y is given, so that is given. But writing it down correctly can be sometimes more difficult than seeing that it is actually true, because seeing that it is true is really trivial, right? Because existence and choices, if you want to write it down completely correctly, then yeah, then you have to have such axioms of how the quantifiers work, and we don't have such axioms, and usually those axioms are only studied in special mathematics courses. I mean, not even bachelor they are studied. Yeah, so let me finish here, And next time we should look at another properties of image and pre-image. Particular, I already forget it. I should write it down. Next up. Yeah, and I should start new board, of course. And I wanted to keep that topic in one place, but okay. Okay, what else? That's one thing. I think definition. Subjective and start. Right. Okay. With that, we are finished, and next time we certainly will finish the topic maps because I'll be on new board. That's why I will be fast, and well, we will have just technical proofs, and there won't be topics about which I can ruminate a lot. Okay.